Hi, so in continuation with our previous videos, we are producing the number 4. Today we are going to discuss about hypothesis testing and type 2 errors. So this is the main, probably whatever you have done in previous are the backbone, and this hypothesis testing, type 2 errors, and later on goodness of fit, analysis of variance, non-parametric methods, regression. This will be your main focus in your journey. You will be doing a lot of this, and it will be based upon those that we have learned previously. Okay, so now why do we need a testing of hypothesis? Okay, or what is it? So suppose you have some idea about your data, that the data has a certain mean of 30, or it comes from this distribution, or it is not skewed. This kind of judgment you have, but to prove this you need certain kind of testing. Okay, so that statistical mechanism, or that testing, statistical testing basically, is called hypothesis testing. Okay, so what happens in hypothesis testing? We'll be discussing the first thing in hypothesis testing that considers, it's basically type 1 error. Okay, and type 1 error is nothing but it's the mishap of falsely rejecting a null hypothesis. Okay, in hypothesis testing, as you already know, that there are two hypotheses. The main hypothesis that we consider is null hypothesis, and the alternative or reciprocal of null hypothesis is alternative hypothesis. Okay, so if your null hypothesis is not true, then it's alternate hypothesis. Okay, so what happens in type 1 error? In type 1 error, which will be the most focused thing, is that the mishap of falsely rejecting a null hypothesis when the null hypothesis is true. Okay, suppose you are drawing one conclusion that there is no similarity between the population distribution of age and height. Okay, and your hypothesis failed, and this hypothesis that there is no relation between age and height, it is basically true, but your data or the sample data you have chosen is failed to prove this, and you get a p-value which is very significant, that gives you the indication that age and height are related. So what you will do, you will add age in your features for predicting height. So this will give you a faulty machine learning answer, okay, or prediction. So the probability of committing a type 1 error is called a significance level. Okay, this thing you have to remember, that what is the probability that you are probably committing this error. This is called a significance level. Okay, so let's start using R for some of these type 1 error. Now the first thing that comes, write with me, that your lower tail test of population mean with known variance. This is the first kind of test that you have to do, that the lower tail test of population mean with known variance. Now recall from the previous classes that known variance means what will be our test statistic. It's the z value basically. Okay, so it's called testing z. Okay, so what happens in this case, that what will be our null hypothesis? Let's write our null hypothesis at as h0, and what will be it? The null hypothesis of lower tail test of population mean will be that mu of population will be greater than equals to mu 0. In this case, this mu is our population mean and this mu 0 is the lower tail of that value. Okay, and we know as our variance is known, so we need z value. Okay, so our z value will be nothing but the mean we collected from let's say x bar that we collected from our sample minus the lower tail value, which is mu 0, because you don't know the actual population mean, as we have discussed earlier, divided by, we know the variance, so variance divided by square root of number of samples. This is what it used to be, the z value. Okay, now after finding the z value, okay, you have to test the null hypothesis. Null hypothesis is nothing but what? That the mu will be greater than equals to mu 0, right? So we can reject this null hypothesis if the value of this z that found from previous is less than equals to minus z of a. Okay, now what is za? Za is nothing but the (100 into 1 minus alpha) percentile of the standard normal distribution, or ND in short, normal distribution. Okay, so if my value, like normally what we use, if you remember, you always use the p values of in case of any standard hypothesis test. So in p value, we generally use the 5%. That's critical value, right? So this alpha is the 5. Okay, so if you put 5% here, basically, so it will become 95%, the za value, right? 95 percentile of the normal distribution. So z cannot have less than equals to the minus of 95 percentile, basically in case of lower, and in case of upper it will be plus. Okay, so to better understand, let's do one problem. So suppose one manufacturer claims that the mean lifetime of light bulb, okay, like to Philips claims that the mean lifetime of a light bulb is more than 10,000 hours. Okay, when it says that it's more than like 10,000 hours, that means it is the lower tail. Okay, if it says that it is less than 10,000 hours, then that will be the upper tail. Okay, so this is our first value. Now they have taken n, that means your sample size as 30. Okay, so in that case, you will be finding one sample value, like that is your x bar, which is your mean of the sample. So in this case it is 9900, not 10,000 but 9900 hours. Okay, this is how you have to frame your problems. Now they have given you that, as we know that we are doing what? We are doing for known variance, right? So population standard deviation is given. Okay, STD equals to 120 hours, and your significance level, which will be alpha, is every time we probably use 5%. Okay, Now your question is, can we reject the claim by Phillips? This is your question. Now how to solve this? To solve this kind of questions, as we said, we have to use hypothesis. Okay, so what is the null hypothesis? First of all, here write down a null hypothesis, which is nothing but that our mu is greater than equals to 10,000, right? So what we have to do right now, we have to calculate test statistics. Just quickly writing down, we have x bar, which is our mean of sample, as 9900. Then we have our mu, which is 10,000. We have our sigma, which is 120, we have our n, which is 30. So from this, for known value of variance, what is the value of z? Because we have known value of variance, we need z value basically. So value of z will be x bar minus mu 0 divided by sigma root under n, right? So this is what our z value. So if we run this right now, we'll get one z value, which is minus 4.5643 blah blah blah. Now what we have to do, we have to calculate the critical value. Okay, so we have alpha equals to 0.05. So for set alpha will be equals to, we have already saw q normalization, 1 minus your alpha value. So for lower case, what will be our critical value? It will be minus z alpha. So if I run this, we will get our minus z alpha is minus 1.644. okay, so if you do one logical test right now, that your minus z alpha is greater than your z value, you will get true. Okay, that means the value of our z is very less than the critical value. Okay, so hence we will reject the claim that the mean lifetime of a light bulb is over 10,000. okay, so we are rejecting the null hypothesis. Okay, so how can you solve this problem in an alternative way without doing much fuss? You just have to calculate the p value, which is p non, and you pass the z value here. Okay, this will do the trick. And if you just type your p value, you know for acceptance your p value have to be greater than or equals to 5%, and you see it's very less than that. The same thing in a very short form. Okay, so we have done the lower tail. Now as you understand the lower tail, you have to do it for upper tail. So upper tail will be nothing but the just opposite, in which upper tail we have mu that will be lesser than equals to mu 0. In case of lower tail, what happens, that mu is greater than equals to mu 0. Okay, and we are doing it for again known variance, so we'll be using ztest, right? Now let's say this time different problem. Or let's do it with the same problem, and that will save your time. So we have the z value previously computed, run, this is our z value. Okay, and what will be the z alpha this time? Z alpha will be nothing but the positive z alpha, because we are doing it for higher. Okay, now if we do z alpha is equal to z, it is also true, so we are also rejecting the null hypothesis. That means in this case, what will be our hypothesis? That mu is less than 10 equals to 10,000. Okay, so one thing you have to remember, if your like significance level changes, that alpha value changes, suppose you took 10%, then you cannot use p-norm. You have to like change the p-norm's default values to recompute basically. Now we have done with lower tail, upper tail. Now it comes two-tail test. That means you have to consider both lower and upper. So in this case, what will be your basically null hypothesis? In case of two-tail test, null hypothesis will become mu equals to mu 0, so no lesser than upper. Then you have to be accurate this time. And as we are taking our alpha equals to alpha, so we are doing one two-tail test, so your significance will reduce to 100 times 1 minus alpha by 2 percentile. Okay, in previous cases we have seen that the percentile is 100 times 1 minus alpha, but this time it is 1 minus alpha by 2. Recall, in case of 95 percentile, in previous videos we have done with 97.5 percentile, okay, for 95% significance, and that's how it comes. Now took one problem. Suppose the mean weight of some penguin found in Antarctica colony last year is 15.4. So this 15.4 is your mu 0. Okay, let's try this directly, right? Now next is that you have taken number of sample of 35. You have found x bar, which is basically sample mean, as I think, yeah, this 15.4, and you have found 14.5. 8, let's say. And they have given, as we are doing for known variance all this, that's why we are computing set value. So you have your sigma as 2.5. okay, so first what we have to do, we have to calculate the set value, which is nothing but x bar minus your mu 0 divided by sigma divided by square root of n. So this is your z value. Okay, first you have to run this. So this is your z value. Then again we have alpha given. We have now this time we have to change the z half alpha will be q norm 1 minus alpha divided by 2, and your range will be from minus z half alpha to z half alpha. Okay, so minus 2 to 2, and your value is minus 1.4194. okay, so we cannot reject null hypothesis here because our value lies between minus z half alpha probability to z half alpha. So another way of checking this is determining your p value. This time it will be 2 times of your p norm of your z value. Okay, as you can see, p is much higher than 5%, so we cannot reject this. So this p value has a statistical term. It is called two-tailed p value. Now this is end for known variance. Okay, now next question comes, same thing you have to do for unknown variance. So just a simple question, if you don't know the variance of your population, what you will do, you will use the variance of your sample. Okay, you have no other option, right? If you don't know what is your father's income or take home is, then what you will do, you will infer from the way you live, like what assets you have, and the same thing happens here. So now the same thing, lower tail under unknown variance. We have same assumption here also, which is mu is greater than equals to mu 0 for lower tail. For upper tail it will be mu is less than equals to mu 0, and for two tail test it will be mu is equals to mu 0, right? So here we will be using t-test, right? So suppose the same manufacturer and question, we are taking the Philips just go above and copy all this. Paste it, the same thing. Change the sigma cannot be as equals to population. Okay, this will, I don't know why, but it's not standard practice. So instead of z, now you are computing t, which is basically the same, but instead of population variance, you are taking your sample variance, right? So it is x bar minus mu 0 divided by your sigma divided by your square root of n. This is your t value. Okay, just run it and then run. So this is your t value. And this time you have to calculate your t alpha, which will be not normal distribution, as we don't have the privilege of saying that it's probably coming from normal distribution. Okay, so 1 minus alpha, and we have to pass the degree of freedom, which is n minus 1. So you get some t alpha, and as it's a lower bound, so minus t alpha will be our measure of interest, which is minus 1.7. So the test statistics, which is minus 4.38, is lesser than the value, critical value, which is minus 1.7. So hence with the significance of 0.05 means 5% interval, we are rejecting the claim that mean lifetime of a light bulb claimed by Philips is about 10,000 hours. Okay, this is how you compute stat when you don't know the variance of population. Now, what will be the upper tail test of population mean with unknown variance? You know the hypothesis here, basically null hypothesis, which is mu is lesser than equals to mu 0, right? So if you put the same thing here, basically in the same formula, like we have t value, we have minus t alpha. So in this case our interest will be t alpha, which is 1.7. okay, so in this case, see the t alpha value. Okay, so the test statistics is greater or lesser. This is your test statistics t value, which is minus something, is lesser than the critical value, which is 1.7. So we can easily reject the null hypothesis. Okay, as you can reject the lower bound, you can definitely reject the higher bound also. So instead of going all this fuzz, you can also calculate the same with p value again, and but this time the p value will be different, as we have used the qt and you have to use the pt function. And if you get confused what this qt or pt is, you always have option question mark. This, as you can see, this is student t distribution. What is dt, pt, qt, rtr, and what are the values, and source and all examples. Okay, now in this pt, what we have to provide, the test value, which is t here, right? You need to provide the degree of freedom, which is n minus 1. You need to provide another that you're doing for upper values, lower tail will be your false. Okay, this will give you a p value for upper. As you can see, your upper value, your upper value is way more than 1, like 5%, so you cannot reject the hypothesis. Okay, that your what's the average life of your lights are less than 10,000. Okay, so what happens in case of lower, we can easily reject that it's not greater than 10,000 years, and in case of upper, it is easily like understandable that it's not going to be way more than 10,000, right? It's basically reverse of lower. So if your lower is rejecting the null hypothesis, that means its upper is going to select that. So if you just remove this one and do this p value, and you can see way less than 5%, so you're going to reject the lower, and in case of upper, it is going to selecting it. Okay, the two-tail test of population, we have done the lower, we have done the upper. Now we have to do the two-way test. We also know how to do that. In this case, our t have alpha will be qt 1 minus alpha divided by 2. Degree of freedom will be n minus 1, and our range will be minus t dot alpha to run it. This will be minus 2 to 2. And our t value is minus 4. Okay, so just again compute the t value. Which is minus 4.4. So as you can see clearly that our t value is not in between minus 2 to 2, that we can reject this hypothesis also. Okay, another way of computing this is computing p value, which will be 2 times pt freedom minus 1 and just check the p value and see it is less than 5%, so we just rejecting the hypothesis. Okay, so that's it for your t test. So you have done 6 tests already. And now the another thing is left is lower tail test of population proportion. As we have discussed the proportion, what are the proportion, why do we need proportion in previous. So you also have to do the same 3 tests for lower, upper, and both. pair for population proportion. Okay, so in this case what will be our lower tail test hypothesis, null hypothesis? It will be that population proportion basically of the population will be greater than the lower bound, which is p0. So p0 is our nothing but hypothesized lower bound, and p is our population proportion value. Okay, so in this case we have to compute the z statistics, which is this p value or p bar. Basically, let's write it as p bar minus limit divided by square root of p0 into 1 minus p0 divided by the number of sample. Okay, so this is what we need to compute again for population proportion. Now let's took one example, that suppose 60% of your citizens, the voting percentage that we have discussed regarding population proportion in previous. So suppose 60% of your citizen is voted in last election. Okay, so voted population is 60%. Okay, now your p bar value, okay, p bar is what? That is your proportion, basically your sample proportion. Okay, so it's given here that 85 out of 148 people in a telephone survey said that they voted in current election. Okay, and your significance level is 0.5. Can we reject the null hypothesis that the proportion of voter in the population is above 60%? As we said that in case of lower bound we will always have to be greater than equals to, so it might be above for null hypothesis, right? So it's given that your p bar value is 85. Okay, your population proportion is given as 60%, that means 0.6, and your p bar will be not 85, actually 85 by 184. Is that because we have done one telephonic survey and you found that out of 148 people that you have surveyed, 85% number of people have voted actually. Okay, your number of sample is 148. So this is your z value. So let's take in bar, let's keep it as bar with p0. So we have all the value. We have now z also, and then we just print the z, and this z will be our test statistics. Okay, if we compute this, we are getting a value of minus 14, right? Minus 14 is too much higher. I think something wrong happens here. So yeah, there was a small typo. So as you can see right now, the z value is minus 0.64. Now if we just compute z alpha, which is q norm in this case, see how it's changed. For first case we compute q norm, then we compute qt, right now again we are computing q norm. Okay, first thing what you have to do, you have to give the proportion, right? So which is 1 minus alpha, and everything is, it's remain like that, and we have to print the minus z of alpha. So as you can see, the minus value, minus z alpha value is minus 0.16. okay, so our test statistic, which is minus 0.64, is greater than the value, critical value, at 0.5% of significance. 0.05%, basically 0.05 means 5% of significance. Okay, hence we cannot reject the null hypothesis that the proportion of voter in the population is above 60% this year. Okay, we cannot, that means it might be way more than 60%. And to do this again with p-value, again do p norm, you pass z, and just forecast the value, and there you go, there's a p-value greater than 5%. So in that case you have to do the upper tail test also for population proportion, and two tail test also for the population proportion. I hope by now you can do all this of yourself. So whenever you have a data set and you have to make some conclusion and you don't know about anything about the data, so what you do, being a researcher, you make some hypothesis, you find the p-value, you calculate the z alpha, and you compute, and you make comment based on that, and you do further analysis. Okay, so this is how you are doing hypothesis testing. In next video we will be learning type 2 error, basically power and beta.